do an example of that. So here I've got some data. I know this is kind of hard to see, but here this is wavelength, and then these are absorption cross sections. Look at that, base E. For Cl2, Br2, and this rather interesting BrCl, I wanted to find a table that had at least some halogens on it. So the BrCl is kind of a weird one. So let's play with bromine for a minute, okay, and calculate the bromine photolysis rate constant. So we notice here, basically, if I were to plot all of these values, if I were to plot sigma versus wavelength, then I would get this. I'd get the absorption spectrum, which is kind of cool. So if I scan through those numbers here, you can see that they increase, that they increase, that they increase. Aha, here's a maximum, and then they start to decrease, okay? So that is giving me an absorption spectrum. And we notice here it has a maximum at, 420 for bromine, okay? So if I was deciding on a, photochemical reaction that I wanted to do involving bromine, I would want a 420 nanometer lamp. And if I had the ability of using a monochronometer, then I would select only that 420 nanometer lamp, and I would calculate my photolysis rate constant based off of that. Well, what if I didn't have a monochronometer, right? What if I had a broad source of light? Well, then I could still use this version of this equation, this sum, okay? And all I'd have to do is calculate a photolysis rate constant at each wavelength, right? At each value, and then add them all up. So here's how this goes. So for now, and this is perfectly okay in your Kinetica simulations. For now, we'll just assume that phi equals 1. That's a fairly reasonable assumption. We're going to say sigma, here it is, it's 64.8. And then look, the 1020 is in front, so that means it's 64.8 times 10 to the minus 20 square centimeter per second, or per molecule, sorry. Okay, now how do I calculate the flux? Well, as it turns out, flux, okay, is pretty straightforward to calculate. It's power divided by energy times area. That's it. Power divided by energy times area. Okay, so the power, we have to make a few assumptions about the power of our light source. In other words, is it 1 watt or 2 watts or 20.532 watts, 8.62 gigawatts, right? We don't know. I have to look at the light bulb and tell you what the power of that light source is, okay? So depends on the light source, okay? What about the area? The illuminated area of the light source. Well, also, that depends on the light source, okay? And typically in a photochemistry reaction, so let's say here I'm going to draw like my lamp, my light source, right? I'm going to draw my like classic looking light bulb here, okay? Definitely not an LED, right? That's my classic incandescent light bulb, okay? And so suppose now I had a beaker that I was like doing my photochemical reaction in. Let's say right here's my beaker. I wouldn't just blast this whole beaker. Well, really, I shouldn't even say it's a beaker, right? We're doing gas phase chemistry. So maybe it's a flow cell, okay? So let's just say here's like my flow cell, okay? So if I was shining all of this light around, it would be really difficult to know what my illuminated area is. So that's why we often use a very technical device called a slit. Simple as that. So it might be like a piece of metal that has a hole in it, okay, with known geometry. And so what that means is now my illuminated area is going to be really well known, right? And so I can use this light source that's blasting light everywhere. But if I want to do a nice controlled photochemical experiment, then I'm going to use a nice controlled like little area like to shoot the light through. So we have to make some assumptions about that as well. Okay. So the only thing we can really calculate is the energy. And this is a nice stroll back into the good old days of Gen Chem, right? E equals hc over lambda. So suppose we were going to use this 420 nanometer photon. Okay, so I'm going to make a couple assumptions here. Okay. Suppose we use a 420 nanometer lamp, and we'll also suppose that it's 1 watt, and we'll also suppose that there's a 1 square centimeter opening. So if we're calculating a rate constant, right, if we're not doing the experiment, we're kind of free to make these assumptions. So then how do we do it? Well, I would literally say flux equals, it's going to be 1 joule per second, because that's 1 watt, divided by, and then I would do, H times C divided by 4.20 times 10 to the minus 7 meters. Okay, so I don't have my calculator up there, but I'm going to do that really quick. 6.626 e minus 34 times 2.998 e to the 8 divided by 4.2 e to the minus 7. Okay, so for that I got 4.73 times 10 to the negative 19. And the units of this equation are joule, and technically it's joule per 1 single photon. Okay? And then now, so it's flux is power divided by energy times area. So now I assumed that it was a 1 square centimeter lamp, right? So we'll just say 1 square centimeter. And so now when I do this calculation, okay, let's see, that number. So basically all I have to do is flip that number because I've got 1 and 1, right? My flux becomes 2.11 times 10 to the 18. And let's see if these units work out, okay? The joule and the joule cancel. And now I've got 1 over photons, which is a photon, per second per square centimeter, okay? And oh my God, I ran out of room here for my calculation. So let's go to the next slide. So Kp equals phi times sigma times flux. So we assume the quantum yield is 1. That's a fair assumption. My sigma was 64.8 times 10 to the minus 20. That's the same as 6.48 times 10 to the minus 19 square centimeter per molecule. And my flux was 2.11 times 10 to the 18. And that's photon per square centimeter per second. And now if we look at the units here, square centimeter and square centimeter cancel. Photon and molecule cancel because with, right, this quantum yield, technically what the quantum yield would be, the unit would be 1 molecule is absorbed, or 1 photon is absorbed by 1 molecule. So we can cancel the photon and the molecule unit. And from this, I'm going to get 1 over seconds, which is a first order rate constant, as it should be. Okay? So we'll say that times 6.48 e minus 19. And so this Kp ends up being 1.37, 1 over seconds, for a 420 nanometer lamp that is 1 watt, that is 1 square centimeter. Okay?